Thank you for reminder, Akos.
All right. Should I
Please.
start? Should I start, Ina?
Yes, please.
Okay. Yeah. Thank you again for the introduction and for also the invitation to have me here as a guest speaker. Yeah, very much obliged to do that. I like to do it with you guys, and also thank you for your interest in being here. Yeah, my name is Volker Wittig. I'm a mechanical engineer by trade, actually, and have spent a few years, over 10 years in the US back then, working on some drilling technological stuff before I came back to Europe, to Germany, to delve into geothermal drilling application and developments. And that all happened here in Bochum, in the Geothermal Center that some of you may know or may have heard of. That has been here almost 20 years. And then we changed it, or not we changed it, but we founded then the Fraunhofer IEG, where I am now currently still involved in the development of shallow and deep drilling technologies and heading up the department here in Bochum. I'm now under Fraunhofer and not as a geothermal center before. Yeah, let's see that this works.
Volker, just a small thing. Would you be able to talk a little bit more louder? I think you are talking on your speaker phones, right? Or headphones?
Can you hear it?
Yeah, it's just when you move head a little bit that the quality is not perfect, let's say.
Okay.
Yeah. So a little bit louder if possible. Yeah, very appreciated. Thank you.
Okay, thanks for letting me know. Let's move to the next one. No, someone that. See where. No,
does it work?
No, not right now.
Okay, let's try to share it one more time. Maybe stop sharing and then one more time.
Let's see where this
it worked 5 minutes ago, people. So yeah, we expect it to be again the case. Okay, perfect.
Okay, maybe I have to do it with the mouse. Okay, that worked. All right, so sorry about that. So now we are working within Fraunhofer, and again, a lot of you, or most of you, will know about Fraunhofer. In Germany, it's the single biggest research institution or alliance working in applied research between university and industry application. And we are altogether about 30,000 employees. Overall in Fraunhofer, among us, we have about 80 institutions. And so we were founded here in Bochum, in this institute, then 3 years ago. Changed over from the Geothermal Center into Fraunhofer IEG, as it's called. And this is our institute now, Fraunhofer IEG. We are well over 200 employees now already, 2 directors, and we are very much present in the west here in Bochum-Aachen area, and also in the east, Zittau and Postbus area connected to the Hochschule Brandenburg. And also we are now setting up a center in the south in Holzkirchen, leading there, especially also with the application in southern Germany in the Klasse Basin. Little bit more look inside our Fraunhofer area now. This is what we do within Fraunhofer IEG. This is the Institute for Energy and Geothermal Resources. So what we did in the past was very much centered here in this part, in this block, in the Geothermal Center. We worked a lot on geothermal energy, geotechnologies, and also geothermal resources. And now within Fraunhofer IEG, we expanded our envelope quite a bit also into hydrogen, work on hydrogen, of course, energy infrastructures overall, and then also on thermodynamic converters, including heat pumps, heating, cooling networks, and also then about smart and digital grids, controlling the energy and regulations, automation, and all of that. So now the part that used to be very much the focus of our institute, has become also larger, quite a bit larger. Like here, you see a picture in the inside part of all that. You know, but we added a lot more stuff and also know-how within the institute. And this is where we are in Bochum. Our Bochum campus, as we built it up about 10 years ago, actually, we managed to set it up with our own geothermal system. Actually, back here is our drill and test site. And this is where the headquarters now for the IEG, and this is also where I'm sitting in this building. And this is very much our downhole, also drilling lab and development area here in Bochum, as it was before. It remained all here. And within our group, within my group, Advanced Drilling Technologies, we have 3 drilling groups now within Fraunhofer. One is the applied drilling groups running really our rig and drilling actual holes. And then we also have one group now that is more drilling engineering and planning for deep wells, people that have been in oil and gas before. And then my group is still very much focused on developing new drilling tools, new way to break rock. You know, you see here our main research point. Today we will talk very much about percussion drilling and also acoustic-based drilling control, artificial networking becoming a big one for our downhole, monitoring our downhole processes that we are developing. So why do we need new drilling technology or look to develop it better? Most of you know it. You know, we have still low rate of penetration, could be a lot better. We have to drill harder and deeper. Typically for geothermal, the tool wear is high, and also you know, the monitoring systems are not that good. So it all makes for not so cheap drilling, so to speak. And this is why we still work and try to develop a better for-purpose drilling technology. And in this part, we will focus on hammers drilling. And we have basically 2 options for that. Look at air-powered hammers that you see up here, or water-powered, fluid-powered hammers down here. And I'm sure you are familiar with both types of them. And air-powered hammers have been around a long time, proving actually how well they can drill, how efficient they can be, and how much they sped up drilling. But on the other hand, they have a few deficiencies. That's why for deep drilling, we are after hydraulic or liquid-powered water hammers. So gas is compressible and much lighter than water or other fluids, other reservoir fluids. That's why the depth capabilities are already limited from air hammers. Plus, we have a lot of very high expansion rates. And for cutting transport, we also have issues with air hammers, you know, bringing up high speeds in the annular area, or we do have problems getting the cuttings out properly. So those are all factors where air hammers are limited to where we can use them and to what depth. And the other part is between air hammers and water hammers. Looking at this chart that we derived from a test drilling scenario that happened in Sweden in 2007, where we were drilling on 2 bore fields side by side with a pneumatic hammer, with a downhole air hammer, Catastrophe air hammer, water hammer, Basara water hammer. Those were all shallow drilling holes down to maximum 220 meters. And so you see here the gray block and the blue block. Gray is for diesel, blue is for water, and the air hammer only needs diesel, no water, but therefore it needs a lot of diesel. And the water hammer needs water and a little diesel. And that was just trying to measure out, you know, the energy and the fuel consumption is. And this is what is known and is also becoming rather important also now in the drilling business. How much energy do I need to drill a hole? And that's where the air hammers are not so good on that side. But on the other hand, they only need air, no extra fluids. If you have them available, it's good. It's good. It may become a problem. And so we have been drilling holes with water hammers also for, I could say 20 years now. This is our project site in Bochum, actually, where we drilled our holes for our campus here for the geothermal power supply. And we used water hammer technology because we wanted to investigate it and just become more familiar with it ourselves, even though probably PCD drilling would have been quite adequate. So we drilled together with Vasara, with a Vasara 6-inch hammer, tried some recirculation out that you see here with a sedimentation unit. And we had another unit actually attached to it to try to come up with at least a system where we could recirculate some of the water to make already drilling possible for deeper projects. And still again, hammer drilling was quite good because we came up with high ROPs up to 1 meter a minute in that type of sedimentary rock types we have here. So that was quite good. And that was another first step into the direction of water fluid hammer drilling. Other applications from the past have been this one here in South Korea with the company Hanjin. They are also building water hammers and rigs, and they also were very keen to use hammer drilling down to greater depth of 4 or 5 kilometers. This is the chart, their ROP that you see here, ROP against drilling depth, and you see it doesn't taper off much anymore after certain depth, like air hammer drilling, where hammer drilling typically goes down still quite a bit more with depth. And the other thing is that the RP is still well over 10 meters per hour, 12 meters per hour for this type of drilling in granite, 8.5-inch open hole. So it was quite fast and good drilling, and also Hanjin tried some recirculation and also some better cutting lift system with using compressed air within that system. Then another few years down the road, we were in Finland with ST1, and the company Anga drilled a deep hole there for ST1 for geothermal use. And the first top section down to roughly 4.5 kilometers was drilled with air hammers, really, and just using air and some foam probably at times. And it worked quite well, amazingly well. So it was also some kind of a record for air hammer drilling, showing that it can be done, and it does come up with still some relative high ROP values, like here, even 10 to 30 meters per hour. So that's quite very good. However, then for an hour kilometer, that could be drilled depth-wise with a hammer. And then the program was planning on continuing with fluid hammers, because hydraulic hammers, they are not that depth dependent. They can be used to about any depth. So then within the same project, some prototype percussion hammers were tried out to be run beyond 4.5 kilometer depth. And then as mud type filters, viscous water was used. So not just clean water, but some light viscous water to help for cutting transport. The hammers that were used, they had a few different kinds. One was from Australia, percussion system. So I just worked with their existing rig and pump system. That was good. And already positive outcome are that, you feel like you're in a much safer environment, less stressful, less air, less dangers from compressed gases, lower air consumption overall. But so this was all good factors, and definitely prove again sorry, how well the percussion and fluid percussion system work. But the problem, one other problem with hydraulic hammers is actually the controllability and to run them at the perfect parameters downhole in greater depth. Here you see a chart from drilling in those wells up north, and you see fluctuation of here's the bit going down, gradually working its way down. Then you see a chart of the flow rate, pump flow rate, and the pressure in the pump, and you see how irregular it is here in sections. This is a timestamp, about 1 hour here in this neighborhood. And this is the problem, one of the biggest problems they experience up there, how to really run these downhole water or fluid hammers to get just the working point right. And that is one more issue to be addressed with these hammers once you have some that work really good, to also make sure you have a means to run them at the proper weight on bit and speed to make sure they function right and give you their best efficiency. And this is what we addressed then in our GEODE research project, EU project with some other partners, where it was about to set up this new drilling percussion-based drilling system, and us building a new hammer section, and also coming up with sensors and data sets to be able to be connected to the percussion section in order to make sure that we have a good control over the system, to have a good and efficient percussion-based running tool for drilling the low wear and low tear and high drilling output. So we set out to completely rebuild a percussion system to make it fit and more useful for use of drill mud and not only clean water, because that was then the main issue that is typically left with the fluid-driven hydraulic hammers. Then you have two options actually with those systems. You can build a flow-through system that you see up here, where all the drill mud and drilling fluid is pumped through the tool itself, and as it flows through, it activates actually the percussion section and then gives you the dynamic forces that you need for drilling. Or the other possibility is to have an external closed loop system, which can be more plug and play, where actually your mud flow powers like a downhole generator or PDM motor, and generates extra electricity or hydraulic energy that then in a separate circuit actually powers your percussion section. And that typically then comes up with a lot of energy losses and lost percussion output compared to the flow-through system. So we decided to stay with the flow-through system for our solution, and then orient ourselves to these initial manufacturers and continue from there. And then there were some others in the past working on hammer solutions or flow-through hammer solutions, whether it be in China, in the US, or in Clausthal, Germany, starting with a continental deep drilling borehole over 30 years ago, 40 years ago, in the coal mining business. So there were a lot of activities for downhole, also fluid hammer systems. And this is maybe the most widespread tool in the industry. It's from Vasara in Sweden. And we have drilled with this many thousand meters. And you see the basic setup here in the view, section view. And you also see here many inside pieces of such a percussion system that you need to make it work. And especially we looked at the inside of it and how they work and how they fail. And then we came up with a conclusion, well, we need the piston here. This is the piston that makes the hammer to what it needs to do, and then the piston needs to be controlled, and there's also happening in wear and tear in the valve section. That's why we decided to really take a new approach on the valve section that you see depicted here. And we decided we need to get rid of it and find something better to control the piston. It's still an axial percussion engine that we have, piston actually moving up and down, so that's something we need, but we can find a better way to actually power it, run it. So we looked around in physics, and then we decided we go back to the quanta effect that you see here, that actually gives us the possibility to use a fluid pushed along the surface at certain speeds to give us a way to control its path, or act much like a fluidic switch on and off. And sorry. And that's what we then further followed and build a switch out of it, like here. So these are the basic hydraulic switches, quanta-based switches that you see. The fluid is being pumped here into this channel, and then it goes either right or left, and it does that depending on how you set this whole system up. So you have only one part left, and that is moving in the hammer. And we were then looking for high flow rate for our hammer, because we need a high flow rate. And don't need a high differential pressure, so we want to have as little pressure loss as possible, and all the fluid we can have, because for fast drilling we generate a lot of cuttings that then need to be lifted up at the same time. And typically, for example, with Stara hammers, the flow rates were too low at full drilling speeds to really get the cuttings out adequately. And also we are looking into variable frequency setups to have a new good solution for down percussion drilling system. And so we set off and started working with switches and setting up what we thought we need. We all first set up a 4-inch percussion system and looked into the feasibility, and this just gives you a little bit impression of how much work we did. Like all these switches here, they are all very different in what they do, how they work, not how they work, but actually the outcome, what they do as far as switching power and switching parameters. But just looking at them from here, you wouldn't notice any different. That gives you also an idea how tedious it is to set up a good system with this. One big thing is the inside of the switch is really the center focus part, because it's the surface area and where the fluid dynamic and the really the salt of the soup is, so to speak. And then surface quality is one issue, but also how to shape the surfaces, and that's what we worked on and got quite some good results that we then ended up making into real metal parts that you see here, and still being worried about the surface area. And the first thing you see already here is that you don't see anything compared to before, and so we had to make things visible always after making the switches with CT scanning to see what we had inside, to verify the tool came out, and then we set it up back for to measure it back after running a few times to look at possible wear and tear. So these were basically these 3 slides here. You see some of the major developments that have happened. One doesn't really see so much, but believe me, there was just a lot of work and development involved. And then we set up here our own percussion system. Like you see here, it all happened at low pressure areas, initially just using plastics, using very rapid prototyping to come up with a system that works well. Because one thing is having a switch that works, and the other thing is connecting. And once you did that, it's down here, that this ensemble work together in a way to fluid that exits the whole system. This is typically what you then feed out the exit of your drill bit and goes back through the annulus and up the hole. This one prototypes that was, I think, last year at the Geothermal in Offenburg. So that was what's inside of our new percussion system is, and then the other part was, of course, to have a kind of forecast of what will happen when you pump anything else than water through it, especially dirty water, mud, drill mud, or even solids within the drill mud. So we started right away with solids. We just did a rough experiments, or actually a few of them here on our test bench, looking here into the into the Vasara part. So we use the Vasara hammer setup just to see what happens. So we've seen it already many times, what happens when you pump dirty water through it. And then this is our basic percussion system as it is set up now, just with a moving piston inside a barrel and very simple parts that are being used to generate the percussion. And then the Vasara, he doesn't just like his solids, you know, we know it, and it pretty much stalls quite fast when you try this. And then our percussion unit, which doesn't need so tight gaps, it's built in a very different way, continued to run for quite a while with despite having sand and solids in the fluid. So it was a very good system. And then we were also very well surprised, but it exactly what we are after. And then our field drilling test was also visible that using some bentonite type drill mud was no problem to run the tool for drilling. So down the road, we then assembled the whole hammer system in the same geometric size as other hammers. So it's a plug-and-play system to be attached to other drill strings. You see the housing here, it's a hammer housing from Drill King or Vasara, from the company. And then we replaced this inside part, this complicated cross section, with this switch section that is not moving. It's a solid part. And then here is the hammer section, the piston, which is actually working in this anvil hammer housing. And here we actually have inserted a box that is capable of being like a fast changing chamber. So we can actually insert different switches depending on what a customer may want, as far as rock type or as far as bit type that somebody may use with a hammer, as far as frequency range goes, or as far as mud type regarding the viscosity in the fluid. So that's an idea to be actually in a position to kind of give the hammer a special fine tuning to where it is to be used or where it wants to be used down the road. And also having the possibility of fast changing system for wear part item. And this is the hammer section all set up together. So how it will be inside the housing, then working up here, the switch system, where the control unit then sits, and then the piston actually sits inside this section. And this is the view of our one of our many tests. This is the new percussion unit with the switch in there. And we actually had here only mock-up drill bit. We were just not interested in drilling fast. We were just interested in runtime, frequency, and matching our piston stroke and frequency to get it in certain range that we wanted. And also what the hammer tool also can run without weight on bit and with weight on bit. Typically, the other hammers are set up that they shut off when you pull off bottom, which is also good and a good idea, but for very soft formation, sometimes that's not such a good idea. So we can also run the hammer the section without radon bit. So we also have the options there. Looking at the result of what we get from the percussion unit as it is set up now, these two important charts: frequency chart, frequency over flow rate, and then the pressure drop, the flow rate over the pressure drop. So one important thing is having a certain flow rate that we need here in the 200 to 300 milliliter range for a 4-inch hammer, which is at least what you want. This is out of our early prototype setup, coming up with a frequency range of 20 to 35 hertz, which is at that time what we were looking at, and it worked quite well for us. The same thing with the pressure drop being still quite high for us. I don't really like to be at that high, but we at least notice that we have a very, very influential parameter that is controlling our pressure drop, and that's really the switch quality inside of our tool, depending on how well the switch is made, or even becomes better as it is wearing a little bit, because it will be cleaning itself more and more. And then we notice that also the pressure drop goes down over time. Quite a bit, can go down significantly. The switch wears down, gets cleaner inside. The second part of the system, which I mentioned earlier, was a sensor and control part. And this is here you see the results of the other partners in our GeoDrill project, setting up a data connection system, mechanical type contact based connection from one side of the drill string to the other through the tool joint. Here in the draw situation here in the real made up first initial prototype tool joint with a brush system here, and these were sensors that were embedded into the sensor hub to pick up vibrations and other sensors depending on which one we put down hole to tell us something about the performance of the tool. And then this was all been tested early in the year on our drill site for drilling performance and investigation. And the drill string part that you hear is just in a very early prototype stage, with something we really don't want to take to the field yet, but as far as being able to hold up to percussion and make and break, it performed really very well. This is just assembly of the hammer section here. This downhole hammer section, we had stabilizers that were also equipped with sensors, and then the data ready drill pipe was up here for the full field test. So coming back to the percussion system that we built, we set up a new mechanical based hammer design for more durability and use of drill mud. We especially were keen on avoiding rubber seals, so we don't have this seal surface interaction, which also always had problems in these tools and lead to downtime. So we try to leave that out. We increase tolerances. We are not really needing this tight exact machine tolerances anymore that are very expensive and also typically lead to low wear, to high wear and low stand-up times. Then simplify the mechanism, reduction of parts. We drastically were able to reduce the part in the hammer, and we can even optimize the mechanism in terms of frequency and impact. piston control with a hydraulic switch. We set up initial system was for 4-inch drilling. So this is the first setup, and the tested frequency that we ended up with was around 36 hertz at 320 liters, and the differential pressure is still high. It's at the high end of things, so we expect it to be dropping down maybe close to 100 bars for these type of hammers, but definitely probably not lower than 100 bar. It was typically then for 5.5-inch drilling. What we are also looking for some possible coiled tubing application with these kind of tools down the road for exploration, drilling, and fast mining applications, especially with flex type coils and also possibly medium deep geothermal drilling installations. And a for-purpose development tool would be the next step for us. And that's something we are currently in the process of doing. And also being able to set up the percussion engine, the hammer, relatively to the application I said earlier, geology and drilling through it, can be, the factors of them can be implemented to set up a percussion tool like that. So overall, those were the things I wanted to share with you and present you today on developments of the downhole percussion drilling, focusing on our new downhole system. And I think I'll leave it at that for now, and then we have time for some questions, I hope. So I turn over to you, Ina.
Very good. Okay, thank you so much. It was a pleasure and a very nice presentation. I wrote already in the chat to people to write down the questions. I don't see any questions at the moment written down, so it's not that many people. And if you want to ask something, maybe you can raise your hand and react. So I will then try to unmute you. For now, I have one question to Volker, and it would be, which kind of, do you see the increased number of companies very interested to this technology, and what are the next steps in, let's say, implementing it and commercializing it? I think that's one of the, let's say, hot questions, how to commercialize it, and when are the plans, so to say, that it's widely available on the market?
Yeah, those are the two questions I probably would say. So we are in communication with two companies, actually also manufacturing companies, about setting up a tool and making one, and building one and using it for more wider drilling applications. So far we have just drilled in our backyard, and I would expect that to go through a few iterations and to have then a tool that is readily available on the shelf for general use. I would say that probably would be another 2 years or so, something like that.
Okay, so yeah, definitely. I think it needs a lot of patience when it comes to everything. And so, could you please just explain how your team works? You are the team lead at the moment of these projects, but do you have as well other people who are dealing with that kind of relationships with the clients and nurturing the ones, or is it again your task to do that?
Well, the outreach to potential customers or clients, or finding them, of course, everybody can do and should do. In Fraunhofer and within other groups that do that. Within our own group, of course, I'm very much probably the first one in the seat to do that, just maybe because I know the industry the best and people. But of course, everybody that's in my team, so especially for a little while longer and goes to conferences or something like that, they are really not pushed, but it's part of that development, hopefully, also talk to people and potential customers to get to know the market, the applications.
Yeah.
But otherwise, you know, I'm very much the initial one doing this, and then so far I have actually 2 deep drilling engineers here. They are also learning Clausthal, they're studying Clausthal and came here, so they're also already quite good into diving in there.
Mm-hmm. Okay, it's good to hear that. We have one question from Mr. Osman, and he's asking, how would this application be different, if ever, in regions where hard rocks are relatively shallower? In example, a very low thickness of overburdened sediments.
In areas where I have shallow, or where I have hard rocks already in shallow depth.
Yeah.
Okay, in shallow depth would be not any problems. I mean, you can run the tool in any depth. The problem with air hammers is you cannot run them in greater depth. But this one, you know, it's very much depth independent. The question for him in that application is probably more, you know, would he, from the economic standpoint, be also okay to just run an air hammer? The rocks are very shallow. You know, probably running an air hammer and investing in an air hammer is still quite a bit cheaper than fluid hammers, than water hammers. You know, the water pumps and rental of pumps, it's not such an issue anymore. They are kind of almost not quite as standard as air compressors, but just almost getting up there. So, but the tool itself, typically the air hammer tools are still quite cheaper. But yeah, so when it's shallow, the rock, I mean, you may be able to drill them with air as well, but you know, using water drilling or fluid-powered hammers, of course, then you're on the safe side that it works.
Okay. Okay, so Osman is appreciating your answer, yeah, and thanking for a presentation. Call out to everyone else in the call. We have a few more minutes. Please feel free to reach out to Volker. Volker also has here his contact if you want to discuss it further with him. The applications in geothermal wells. I think it would be beneficial for you then to reach out to him. I know that he will be very happy, and as well welcoming to students' internships and master theses and PhDs. I know that you offered a very wide range at Fraunhofer, from reservoir to drilling. And at that time when I applied, that was in 2014-15, I think you offered very interesting projects.
Still, it was a few years ago.
Exactly. Yeah, exactly.
Yeah, so please contact me if you have any questions or inquiries or something about Fraunhofer or drilling or something else. Geothermal. Geothermal applications are really pushing now, but drilling is not the problem. Mainly getting the finances going and the risk assessment done right.
Yeah, exactly.
That's major drawback right now.
Can you comment maybe the everything what's going on in Germany now in terms of geothermal and collaborations of different companies and some innovative technology? What do you think? Where does everything go? So we see which direction everything is going, but at which pace?
Yeah, I mean, we came out with this little study that we did, our roadmap for deep geothermal and shallow geothermal, where we pointed out the potential and what we could need and use in the future. But now the gold rush, the big gold rush, has not really been started. But you know, the inquiries definitely have gone up of even small municipalities as they have to do their heat planning now in Germany. So that's a political decision. Each municipality, they have to do their local planning of heat. their localities, how much heat they use. So there's already the reality that everybody now has to start thinking about and differentiate between the kind of energy what do I need. And heat and cold is a big one, and then the rest is whatever industrial processes, transportation. So that's number one. You know, that means everybody's thinking about it, and then the other question is we have a lot of questions you know, regarding how can you use geothermal. Everybody calls how can I use geothermal in my area. So we have a lot of inquiries, but then things really getting done, you know, it's still very, very slow. Very slow due to the, you know, two facts, the high invest and then also the shared risk, which is not there yet. You know, that we have a way to, if you have a dry hole in deep geothermal, that somebody does not go bankrupt, but that you have a system in place where it is actually federally insured or something like that. The other one is now also the starting and additional production of metals and heavy metals with the brines out of geothermal waters. You are probably familiar with the company Volker that is advertising everywhere and also in the Oberrhein quite active. We still have to see how much they actually pull out, but you know, adding some more value actually to the lift or to the mining of geothermal energy, which is a very low density energy compared to oil and gas. So, you know, it will just not be as will not give you as much finances or return of investment as fast as oil and gas did. And the other one is that we have, of course, Bavaria, Munich, they're being our big showcase, and they continue to be quite successful in expanding their use of geothermal power there, which is very good. So that always brings a big push. And then also, as you have heard, probably the company ever launched their second and now largest project in Geretsried. And I have to say, sorry, just a bad cold. So, and they've been able to, you know, start drilling already this year. And I hope that it may also speed up our process for the rest of the country towards the use of geothermal energy. We will see. But it took an external company, foreign company coming to Germany, but they drum up their own money. They were quite successful in finding investors, so they were persistent enough. And now 2 rigs are running parallel to try to establish a good deep geothermal system.
Yeah. So what they do is basically they drill a lot of laterals and then they connect in the middle, and this is how they optimize, so to say, the temperature, the heat, the heat exactly. Intake.
Yeah. So whatever actually promises is that they promise you an output of thermal energy because they are drilling a subsurface heat exchange system in a big way. So they, you know, that's what geothermal based on, basically getting out heat, and therefore you need somewhat of an heat exchanger, and that's what they're installing by drilling a lot of laterals, as Ina said, and they do it now in a special way using your directional drilling system that you know from oil and gas drilling, then also ranging tools that are there. So nothing new, but they just use everything a lot into the limits to set up downhole heat exchanger system. And that's where they take the risk out of geothermal as far as the flow rate goes, because that's typically the highest risk. What are we after in geothermal is 2 things. It's temperature and then flow rate. And from that, you know, thermal energy you get out. And typically the temperature you can forecast more or less quite good. You know, 1-2 degrees up or down. but the flow rate can be from nothing, from
Yeah.
0 to hero. It can be nothing, and it can be also right on or not. And that's why they just said, okay, we need to take that out of the equation and make sure we always get what we want. So decided to do horizontal.
Yeah, very interesting area that we live in at the moment, I would say. We have one question which is pointed out to your technology, and the question is, can percussive drilling be safely combined with PDM and MWD? And are the vibrations of percussive drilling impacting performance of PDM and MWD during operation? And are there any limitations there?
Okay, combining percussion drilling with MWD and motors, actually, basically. So that's why I integrated this this performance, the development of our sensor subsystem, which is actually basically also for our MWD setup to have drilling data while drilling and accurate drilling data from the direct BHA, not just collected on surface. So that is basically also done to have rugged sensors, rugged enough sensors that withstand the percussive powers, and also on the other hand, the rotation units. We don't know yet. That's the next part we are after with the coiled tubing drilling application, to have more the combination with a motor, with a downhole motor drive. We have only initially tested it, and it was, the results looked positive, and the other thing is we have the ability to kind of set up our percussion engine to be in favor of one or the other. We can make it more fast moving with slow impact, or we can make it slower moving with high impact. And that way we can also fine tune the rotation unit going with the percussion unit and make it a more efficient and longer lasting setup.
Okay, thank you very much. Well, this will all be dependent on the rock at the end, right? Where do you do it?
Then the feedback of the rock will also be another parameter in this.
Volker, are you going to be able to share with us some slides, maybe partially or completely the slides that you shared with us? The audience asked about the slides, and it will be very much appreciated if we could share it with the audience.
Yeah, I would say yes. For probably 90%, I can probably share. I will just look at them very quick, and then I send it to you as a PDF, right?
Yeah, perfect.
Yeah.
Just another question came in. Yeah, let's use a last question for now for this presentation. What is the highest deviated angle possible to apply, and what are the limitations of DLS for percussive drilling?
Same so far as what you expect from other hammer systems so far. So we did not change that. And as far as thinking into directional drilling, as far as what DLS, how little you can build up, I would say we don't know it. We don't have it tried out. But as far as the tool is built, just from the geometry, it will not be any worse than other tools because it's not longer. It doesn't have an extreme length or something like that. As far as within the rock breaking and drilling scenario, with making the curve in a shorter or in a greater angle, that needs to be seen. But I would say within the same range as what people are used to now from percussion units.
Okay. Thank you very much. I hope this answered all the questions that we had so far. It was really a pleasure and always an honor to discuss it with you, Volker. And yeah, keep us posted on your recent developments. We are eager to learn and to exchange, especially, you know, it's a very hot topic at the moment. And yeah, we look forward to welcoming you again. And we appreciate a lot your time and your effort to share your new developments with us.
Yeah, thank you very much. It was my pleasure, my great pleasure.
Thanks, everyone. I will stop recording now just for the case. And yeah, it will be possible. We will send you later the link where you can maybe have a look one more time, have a look at it.